this exercise, I think this model, so it's the agents course. If you guys have registered to it, you should probably see this, or I'll attach this notebook. Um, so here we are calling this model Llama 3.2 3B instruct. Okay, so this is a gated model. So there are some gated models and others are kind of free models. So gated models, Hugging Face. So these are gated models. To give more control over how models are used, the hub allowed model authors to enable access requests. So you do have to request access to work on few of these models. Okay, so these are it's generally a form that you have to fill up, and then it will provide you some access request, and it usually takes within 24 hours you get that request. Okay, so all of you, when if you are working with the Hugging Face, which you should have to, so when you log in, you do go over to your account, right? So in your settings, okay, settings, and here you go for you request an access token. Okay, so you need to. So right now I do have an access token over here. So I will use this access token. So any email ID that you are linking or connecting with your Hugging Face account, you can actually go for access token. Okay. So here, once you have the access token, the best way to go about is, because I like to work with Colab. So you can have your API keys, so API key token set up here in your notebook access. So when you click on this key, you can write your access key name and then the value. So all of these, so this is my API key for Vertex API, for example. This is my Hugging Face token. This is my width and bias token, right? So you can keep adding your secrets over here. And when you are using the Colab, all you have to do is from google.colab import user data. Okay. And then just import and then use the user data.get, so that will get the key HF token, and then now this is the token value which you can start using anywhere you want. Okay, so Hugging Face will actually probably, where did I use this token? Yeah, so it will validate the token and then you can start using it. Okay, so sometimes so this is yeah, so this is the agent's notebook. I'm not going to describe the notebook right now. Yeah. Okay. So anyway, so it just validated over here. And okay, let's just enter. Oh, you were okay. Okay. So I put it in the environment. Again, you can just use that. So here, let me use a token, which is, for example, right now, to delete this token, and probably I might not get access with this one. I'm trying to generate the error that you might see when you are new to the Hugging Face. Let me see if I can generate it. Now it's still, I think I do have access to that one. Anyway, so if you have a problem like this and it says 403 not available or something like that, yeah, actually I have it. That's good that I can show you. So it says that the model, the 403 client error forbidden. So this is a gated model, right? So you probably have to cannot access gated repo to URL. Okay, to access the model, and you are not authorized. Okay, so make sure to have access to it at probably. Then we might have to click here, and here you will get the access. So you'll have a community license agreement, and then you'll just have to go down, and then you need to. There's a form somewhere over here. Okay. Okay. So I think, yeah, there is the form. The information will be collected. Okay. Yeah, I'm logged in over here.
Ma'am, I think you have to go in and expand to review and access.
Yeah,
That is
you are right. Yeah. So over here. Yeah. Yeah. So here you have to access. So you have to provide all your access information. If you can put a student, that gets you access quickly because they don't want you to use commercially. So yeah, and then you access for it, and then within a few hours you get the you'll get it. Okay. So that's how you can use your gated models. Okay, and then this problem will be gone. So whenever you are using Hugging Face or any kind of token with Colab, this is the best way. So you can also keep your tokens hidden, right? So so that's a good way of keeping your environment also kind of secured. Okay. So try using it this way rather than some of my notebooks might have unintentionally I've just being lazy and just use the token right away. But my request will be if you see something like that, don't use like it. You should actually use it as a secured environment and then use it as a token variable, okay? And put it inside your Google Colab access key and then use it as a token. Okay? Okay. So I hope there's no more questions on this. This you can solve, and I will. So in this course, we will be adding new materials after every 2 weeks. So there's a lot of materials. So I'll also keep announcing once I'm posting this new materials over there. Okay. Okay. Think that is good. I wanted to touch base on a topic today, which is about positional encoding. So as we are developing this self attention, and today I will discuss a little bit about mass attention. Um, we want to create. So the first thing is 2018. I think, yeah, 2018 BERT was developed after the transformers came in. So first we will try to develop BERT or T5 kind of model, the older generation models, and then we will try to use a GPT model. We will also try to implement a very simplistic GPT-2 kind of model. And then finally, as I mentioned, our goal is to also learn few more concepts and implement the DeepSeek model. Okay. So, but before that, there is a basic difference between your sequence model and your transformer-based models. So, sequence models are open a PowerPoint. So, sequence models, as you know, they are kind of a state dependent, right? So state dependent, and that's the reason they are slow, because they have to remember all the states they are. So this is for t minus 2. So this state is connected to t minus 1, right? And you have to keep remembering all your states over here, right? So t, right? So like this, these are my sequence to sequence model. So here, because we are sequentially providing a word, we are sequentially providing words. So there is, the model knows how the words are arranged. Okay. But in case of my transformer models, for example, I'm not providing really the sequences, and I'm giving all the words together, right? So I'm just providing the word, I love pizza, right? So it doesn't know it. So it's because it's trying to find a context in my attention model. We are trying to find a context rather than the sequence. We are trying to find a context or how these are related. So in the last class, I was trying to mention that how each of the words, how much percentage of each of the words is again available to another word. Okay. So how much of this pizza in your final value contains I love pizza, I and love, right? So these are few things that is providing me context, but at the same time, you need to remember how the positions are encoded. So how is this word or how is this sentence, or what is the sequence of this word organized? So that's the reason I discussed about word embedding. So we'll talk about positional embedding. Okay, so it's a positional embedding. So how do you define this positional embedding? So I love pizza versus this is definitely different. Like pizza loves me, right? Pizza loves me. So this is of course different. Pizza loves I, for example, right? So anyway, so these are two. So we will talk about how we. So there's positional encoding done. Okay. So there's few different ways that you can work with positional encoding. One of them is called yeah. So in a sequence to sequence model, so I think I did just told you about it. So how do you train a transformer network using multi-head attention? So we haven't discussed multi-head attention, so all these things will be coming in this transformer course. You feed your data into the model all at once. While this dramatically reduces the training time, there is no information about the order of your data. This is where positional encoding is useful, and you can specifically encode the position of your input and pass them to the neural network using sine and cosine formulas. So that's the equation. But why do you use sine and cosine formulas? So for example, if I was to use this, so I can use 0, 1, and 2, right? Along with my word embedding. So along with my, let's say this is my word embedding 1. So I can simply use this, right? I could have simply used it. Word embedding 2 and plus this, and then plus word embedding 3, let's say. But why do I use a sine and cosine kind of so why do I use sine and cosine? So this is a very simple basic one. Why do I use that? So the reason being your sine and cosine always is within the range -1 to 1, right? So for any sine angle or cosine angle, the value will lie between -1 to 1. And it's also frequency dependent, right? It's also omega or frequency dependent. So if you look at this, so that's the reason we do not blast our positional encoding. Otherwise, if you have a word with a 1048 kind of token size, then you'll be blasting it with a very huge number of huge value, right? So which we do not want. And that's one of the reason we make it like -1 to 1. And that's kind of one of the positional encoding ways. And that's called the sine and with the cosine and cosine formula. So if you have sine of some angle, sorry, yeah. So here you have a sine of some angle and cosine of some angle. And then D is the dimension of the word embedding and the positional encoding. Position of the word. So we'll do this coding right away, right now. So it will be clearer. K refers to each of the different dimensions in the positional encoding with I equals to K divided by 2. So to develop some intuition about positional encoding, you can think of them broadly as features that contains information at relative positions of words. Conversely, the value of sine and cosine equations are small enough between, as I was mentioning, between -1 and 1. That's when you add the positional encoding to the word embedding, and you do not significantly distort and instead enrich the positional information. So how this kind of equation you can think of is this is my first word with position at position 0, and then it has some I, the dimension of frequency of each embedding, for example, and the total embedding size is D. So you can kind of think that so this is the word embedding size, or so it's defined with 5 different vectors, and then these are different I values, and this is at the position 1. So also let's think of, let's try to check with this sequence, I am a robot. So the index of token, so the index of token K, so I is at position 0, am at 1, 2, and then this is at 3, right? So the positional encoding matrix width, so we are thinking it of dimension is 4 and n is 100. So you can actually calculate a matrix, calculate a matrix corresponding to this. Okay. So yeah, so let's actually, so this is given in your I have uploaded this to GitHub, but let me actually go and try to write this from code it from scratch. Just give me a minute. So this is a better, these codes are better, so you should follow that, but this is a simple, just a quick technique I want to, or quick way of writing. So positional encoding, let's call it like that. Encoding. And here we want to give it a position, right? And d underscore model, and then n equals to 100. Okay. So we can, so n is usually this value over here. So you see this huge number, that is basically n. Okay. So we can actually write this as sign for position in n 2d by I. That one, yeah, sorry, my bad. 2I by n. Okay, so that's kind of the way. So we're going to code this right now. Okay, so we can pass position and gives my size of my dimension size basically. So then, so we'll have the position. The position is actually position of the word, right? Position of the word in the sequence. Okay, so it's already sequence on d underscore model. Hmm. The dimension of the word embedding and positional encoding, and in maximum number of positions. So that's kind of the way. And then you return an array. So we want to return this. Okay. So just want to return it, and we can then go for more arrays, and this is how it looks like. So just going over a smaller example over here. So we can do first encoding. So just a numpy. Fine. And then for I in range of start from 0, comma d, and for every even number. So it's an even number. So encoding MP position in star star I minus I by D model. Yeah, this is for the sign part. Okay, this is for the sign, and then we'll go for encoding. And then if I plus 1, yeah, that's done. So this is for the cost part in star star. That's right. Yeah. So this is sign is I and I plus 1. Yeah. Okay. So for or sorry, that's not the right one. It's actually for the odd and even. We are separating out from the odd and even values. Okay. and return encoding, that's fine. So then d underscore model, we say 4, n equals to 100. And we want to encode this, right? I am a robot. So over here, then we do position equal to, let's put 0, 1, 2, 3. And then for positions and positions, okay, then hopefully this is fine. Let's check. Not doing that. Okay. So see, this is how 0, 1, 0, 1. So just first one, the first position, then second, third, fourth. So this is how you can simply generate your positional encoding, and then this encodings you can then use for your use along with your word embedding. Okay. So now for the last part, I'm going to discuss a little bit about again my self attention, and this time we are trying to build everything, bring everything now together. So earlier we studied about self attention, right? So this is self attention QKV. So query key value equals to softmax QKT. So query key, which is this we are where we are trying to generate the similarity score divided by the dimension of key. So that gives me the value for my the scaled similarity score into value. And finally, this is what I was trying to discuss last class. So this is after the implementation. So let's see. I think I'm missing that part. Let me check. Yeah, I think that's one. Yes. So this is the slide I was talking about. So because we are trying to find self attention is actually the multiplication of a word with itself and other words in the sentence or in the entire context or in the entire tokens that you are passing to the model, right? Which could be in your training set, for example. So here, when we calculate the final scaled value of query and key into the value of matrix, so inside the matrix value, we calculate that 36% of the first value is coming from pizza, then 40% of the first value is for is, and we calculate 24% of the first value is from awesome. When we are trying to calculate these matrix values, so this is my value, and when trying to calculate this, we are actually defining it with how much is each contributing. So pizza along with pizza is not or let's not complicate that way. So pizza is kind of contributing that percent if it's 40 and 24. Okay. So each word has a contribution in the value matrix. Now this was the implementation. So this implementation is provided. And today we will go over and talk about or think about a little bit about word embedding. And then I already defined what is positional embedding. But let's think of a little bit about how these word embeddings were created. So in the class, I was mentioning that when you have something very similar to each other, right? So pizza is great and pizza is awesome. So these two sentences are very close to each other, right? Because great and awesome are synonyms of each other. In when the two words are used by itself, they have a slightly different meaning, but they are kind of synonyms to each other, right? So we want to establish the fact that our model should know that similar words should have similar vector values, right? It should lie very close to each other. And that will help my neural network to learn it more efficiently. So this is where we bring in our neural network training, and which can now kind of start learning that these two are synonyms, right? Also, the same word can be used in different contexts or made plural or used in some other way. Okay, let's just move over here for a bit. So here, let's think that I am defining only one number with all these words, right? So there are, I'm not sure, maybe 60,000 or some kind of English words in the dictionary. So each word can be given a value like this, right? A positive or a negative value. But, and that way, great and awesome can also be given some values. And within my one-dimensional space, they can lie somewhere in between, right? But when you are using it in a sentence, what happens? We are using a different context, or made we are using plural form of it, or it might be assigned in some positive or negative connotations also. So, for example, the word great can also be used in a positive and negative way. Like pizza is great, my phone broke, great, right? So that's a negative connotation. So the number of ways we keep increasing. So why do we need a word to have more dimensions to it? So why do we want that? So so just because a word can be used in various different contexts, right? So it becomes necessary for us to have to write it in terms of a vector, right? So to write it in terms of a multi-dimension or more than a number, right? So maybe minus 2.5, something like that, right? So represent our dimensions in a number of vectors. So we can bring this similarity, or we can train our model to bring these similarities together, right? So how is this word embedding? So let's build a simple word embedding network for two phases. Okay, so we are giving only two values. So the first is create an input of a simple NNN. So for a simple neural network, so let's say this is my training set. Pizza is great and pizza is awesome. So this is my training set where my model is trying to learn that great and awesome are two similar words to each other. Then we create an output, connect all the, so first we create this, and then we also write the output over here. So the output, so remember, our neural network's goal is always to predict the next word. Okay. So with that next word prediction, is it doing a good job in getting these word embeddings corrected? Okay. So anyway, connect all the inputs to at least one activation function. So now we pass it to a softmax layer or activation function ReLU, not softmax, sorry. We'll pass it to a ReLU layer, and then finally connect this activation to an output layer. So here, when we connect these, we are actually randomly giving some weight, because weights are the ones that we want to train in this model, right? So we are giving some random weight values like this. So it is accompanied with, because we have two softmax layers, so we have two values for pizza. So this is coming from, let's say, the embedding 1, and this pizza 0.13 is from embedding 1 and 0.14 from embedding 2. And this way we keep building it for different words, right? So those weights are word embedding values and are randomly assigned. So for in the beginning, we are randomly assigning it, and then we are calculating the cost value over here, because if we will know our training network is perfectly trained when it will identify the next word after pizza is, right? So this is my simple network or trading procedure when I calculate the cost function, back propagate it, and then again I try to update my weights. Okay. So this is the way I can update my weights, and then once this weights keeps updating, then you will see that great and awesome clumps closer and closer to each other. But the plan is to change them using a training data. So randomly assigned, but we then use a training data to modify this, right? So in your initial phase, so the bottom word embedding and the top word embedding, for example, let's say, so is awesome pizza. So because it's getting a randomly generated value. So let's say this is my randomly generated value. And then is great awesome pizza, and here see it has a very it's lying very quite at a distance to each other, right? The awesome and great is really lying at a distance to each other, and it says there is no similarity between awesome and great at this point because it's randomly initialized, right? So what we do is, as we keep training this model, the model tries to learn that awesome and great are very similar to each other, and they are getting similar word embedding. So in this process, along with our training, as our training process proceeds, this is where our word embeddings gets trained and the similarity keeps appearing, right? Okay. So now we will, so I hope you got a little bit understanding of how these word embeddings, how these word embeddings are, you get the word embeddings. Yeah. So let's go back a little bit about the architecture for self-attention, and then we will talk about the architecture for mask attention. So self-attention are usually used in, how do I say, classification processes. So you can classify a text as sad, happy, or sentiment analysis, like logistic regression analysis, kind of. And the decoder part, which we will come after we talk about mask attention, is actually what deals all your most of your language models like ChatGPT is using, is a decoder model, okay? Because it actually helps in predicting your next word. So my language models are mostly my decoder models. But when you are using a classification problem, sentiment analysis, and things like that, you usually use a encoder model, and encoder models have this self-attention built within it. So how do you use this encoder? So you have a word embedding, then you have a positional encoding, right? So I just talked about positional encoding, and then you pass these values to query value and key and calculate the self-attention scores. And then finally what you get is context-aware embedding or contextualized embedding. So these are finally, this gives you some context. So the self-embeddings are able to get context out of your tokens, right? So that's kind of the goal for self-attention. Now, so it can so context embedding clusters can also actually they embed words and they can also embed similar sentences and even cluster similar documents. So they are used for, you can use them as a kind of a similarity clustering also. Okay, so it's kind of an unsupervised cluster problem. Let's think of it. So you can actually cluster them for words, you can cluster them for sentences, or you can cluster them for documents. Okay, so similar documents. Now this is again again iterating the encoder only transformers that not only use that only uses self attention are called encoder only attention. The context aware embedding that the transformers create can be used in a variety of settings. So what are these kind of settings? So the settings that you can use this transformers are, so in the different settings you can use this transformers could be your like sentiment analysis, yes or no, so some yes or no type of questions, yes or no. Okay. So these are encoder only models. So for next few classes, we will focus on separating this encoder and decoder only models, and you also use encoder along with decoder. So encoder in vision models, encoder decoder, the unit, I think everyone heard of unit. So unit is a encoder decoder kind of model. Okay, in vision. Okay, so yes no sentiment analysis, and then so this is your encoder only model, and this is my decoder only model where instead of the self mask, sorry, this is wrong. This has to go. So masked attention. So instead of the self attention, we are using masked attention. So everything remains the same. Word embedding, positional embedding. However, we are just using masked attention over here, and this gives us generative input. So that's the reason you call this as generative models, right? So your ChatGPT is a generative model because it can generate new inputs, or it's trying to predict the next word. It's always trying to predict the next word in a decoder only model. Okay. Okay, so let's try to take a look about what is self-attention versus what is mask attention. So let's take this sentence. So pizza came out of the oven and it tasted good. So in the beginning of the class, we were trying to establish the context, right? So how or which word is it referring to? So it is referring to pizza, of course, right? So going over the self-attention, we were trying to build those attention scores, right? Now in self-attention, the is actually kind of getting a similarity. So you calculate the similarity value of the with it, pizza with it, came with it. So every other word is actually kind of getting a similarity score with itself. Okay. And but over here, when we come to the when we are in the mask attention, so it looks at the word before the word of interest. So if this is the word of interest, so all the values or all the similarity scores are happening to the word that is before it. It is not calculating anything with tested good. Okay. So it's not going to calculate anything with that. So it's removing this tested good value. Okay. So what will happen to the word the? So if I'm trying to check the in self-attention versus the in mask attention, so in mask attention, then what do you think will happen over here? So if this is my word along at which this is my word of interest, so then what happens?
In the
So
first
it doesn't,
one, we have to write the whole sentence, but in the second one, after
it's
writing
just,
the half sentence, it predicts the complete sentence.
Yeah, so what happens to the, so yeah, you can even think of this the, or if think of this
Uh,
the, yeah,
ma'am,
yeah,
like
go ahead.
in the first one, it is referring to the good, and the second one is
Mm.
only referring to the pizza.
No, my word of interest is it. So this is my word
Oh,
of
okay.
interest.
Ah, okay,
Yeah,
yeah, yeah.
yeah. So this is word of interest. So that's the reason it is getting a similarity score with all the words that come before it and also the words that come after it. However, here when you have a mask attention, it's only getting a similarity score with all the words that is before it. No word after it is contributing to it. So that's again the reason why it's the generative model, right? So it cannot see the, or it's not given the word that is after it, after it. Okay. So yeah, so if you think of this word it gets a similar, sorry, if you think of the word the, so it will get all scores, attention scores from all the words from here. But if I'm thinking of taking this word the in this position one, it doesn't get any attention score from any of these words. So no attention value coming from these words, but only for itself. Only the is like by itself or the self attention. So it gets a similarity score of the with the. Okay. So kind of we'll talk about this next week, but you can think of the matrix something like this. Um, so everything kind of it's a lower matrix, so it doesn't see any word. So if I say pizza is awesome and pizza is awesome, okay. So pizza has something, then is also sees this, but there is all the values are zero. So is cannot see awesome, okay, but awesome does see awesome here, okay. So all these are kind of the lower bound metrics, yeah. So they have values over here. They have values here, but no values at the top. Okay. So that's kind of my mask matrix. Okay. When we'll talk about a little bit more on the matrix calculation. Okay. Yeah. So this is how it sees. It doesn't see all these words. Okay. So finally, the decoder-only transformer will do a good job at generating prompt responses because it cannot look ahead. This is why ChatGPT, which is a decoder-only transformer, is a generative model because it's specifically trained to generate the text that comes next. Okay. And this is how your finally attention KQV softmax and then yeah. So here it's a mask matrix that you add because you have to uh, kind of limit it not to see the next value. Okay, so you limit it over there and it doesn't check the next value over there. Okay, so that's how your mask attention. So now to generate these models, we will now start coding. We'll talk about mask attention next week.
Hi. So today in our regular algorithmic class, we will be discussing this problem of implementing a hash map from scratch. So let's look at the problem and then I will explain how there are many solutions, but one of the solution that I picked is a little bit easier to follow and also it has a good time complexity, so we can probably use this for a future purpose. So it's a deep code problem. So let's look at the problem now. So designing a hash map. So design a hash map without any built-in hash table library. So implement the hash map class. So implement the hash map class like this. You have these methods. So put, get, and remove. So void put inserts the key value pair into the hash map. If the key already exists in the map, update the corresponding value. and in int get returns the value to which the specified key is mapped. If there is no value, then you return -1, and void key removes the key and its corresponding value if the map contains the mapping for the key. So if you have the value, then you remove the value. So that's how that's how the problem is designed. So that's the my hash map class with this following method. Okay, so just go over the input and the output. So my hash map, and then first we are declaring a hash map, like a new hash map, and then we are kind of trying to get if you have 1 1. If you have the key and the value 1 1 inside the hash map, then you return. So you don't have it. So you have, then it returns null. Then 2 2, it's not there, so it returns null. Then you get, because it's returning null because it's at the same time updating the hash map with 1 1 2 2, and then so when you call the get, so it returns 1. So get with 1, it returns 1, which is at the index location 1, because you have already updated or put the value into the hash map. So it goes like that. So if you remove 1, get 1, so it just goes like that. Okay. So for this purpose, even though it's not really mentioned, so the constraint over here is key less than equal to, so 0 less than, so it starts from 0 and the value can go up to 10 to the power 6. At most 10 to the power 4 calls will be made to put, get, and remove. So right now, with my solution, it can go up till 10 to the power 3, that is with, let's think of the size between 0 to 999. So here, also notice that, because you know in a hash map you can also have a key as a string, but these are the constraints. This is actually a little bit easier because you have int key and int value. Okay, so the key is an integer and the value is an integer. So we can make use of a property called modulus, with which we are going to provide this solution. So the solution will basically use so in the main property that we are going to use here is a linked list. So it's a linked list and a modulus property. Okay. So how do you actually use a hash map, or let's say, how do you populate an hash map? So we can have it as index and value. So if we have an array, so with location 1, 2, 3, value, let's say A, B, or my bad. It's because it's an integer. So let's have the value as 100, 101, 102. Okay. So then this can easily go over here as 0 has 100. 1 would be 101, and 2 is 102. Okay. So that can be one way possible, but we don't want to do it that way, and we can simply kind of take a value of modulus, and that will kind of give us O of 1 if it is good. So O of 1 complex fitting or at max it can have a complexity of O of n. Okay, so let me try to now get over to the problem. So as I was mentioning, my constraint is I am actually having elements, or I will be using elements between 0 to 999, right? So, or I will have around about 1,000 elements. Okay. So how can we take a key value and map to an integer between 0 to 999? So my goal is to take a key value and then I need to map it between 0 to 999. Okay. So what we can do is think of the concept of modulus. So if I have 100, let's say, divided by 1000, okay, so that's the number of elements I'm going to have here. What's the modulus going to be? It's going to be 100, right? Again, 1100 divided by 1000. So the modulus is going to be again 100. So you might say that if I'm taking these values as key, then there is going to be some form of collision, right? So the same key basically, so I'll actually end up with the same key, right? So we'll definitely have to deal with that. But if we still move on and say 0101, so that is going to be again 1, right? So 102 modulus of 100, 1000 is going to be 2. So I think you got the idea. So, so now let's think of how we can possibly avoid this problem of collision. Right, so that's my biggest challenge here. So one of the ways we can go about is by using chaining. Let's say chaining. Okay. So what is chaining? So we can chain, of course, chain some nodes together like this. Or maybe node 1 plus node 2, things like that. Okay. So if you look at this, what does it remind you of? It's kind of the linked list. So this is how you can, so the first node is actually pointing to the second node, right? The second node is pointing to the third node. So it has a memory and it has a pointer that is pointing to the third node, and it also got a value by itself. So by using the property of linked list, we can try to conceptualize this problem again. So let's say we have en value again, right? And then we are given, let's say 100. So key value of 100, and which should have a value of 1, and key value of 1100, which got a value of 2. Okay. So now, how can you input this in this key value location? So if I go back to the problem of that modulus, so 100, of course, divided or modulus of 1000 gives you what? 100, right? And then again 1100 modulus gives you again the same value, it's 100, right? So it gives you the same value. Now, if you think of this, let's store this entire value in a linked list. So 1, so that's the key, and which is pointing to the next node, which has a value or key value of 1100 followed by 2, right? So I'm actually discussing about the put method. So how do you put this value? Okay. So we can store the nodes because we don't want to lose any information, and in the put operation, we can simply do this. And then if you are trying to find with the, let's say with the key value of 100, then we come over to the key. So we find the modulus. So that brings us to the key of 100, and then we try to look into this linked list, which gives me the value of 100 comma 1, right? So that's the value. So my value is 1. Okay. So I think that's kind of established. Now, how do you go about the method get? Okay. So let's go over key again, and then you have the value. So it's 100. That's my key. So the first node has 101. And it's kind of pointing to 1102, right? Okay. So we go over the linked list, and if we find the key, so we go over the linked list, and if we are finding this key, so let's say we are trying to find 1. So we are finding this list, we just return, right? So we return value of 1, right? If you are trying to find or let's say I'm sorry, let's do 100, right? So we find 100 and we return the value 1. Otherwise, we return the value. So if we don't find it, we return the value -1, and then we finally exit from this, right? Lastly, our other condition is how to remove. So we want to remove the value, right? So we got key and value here. Again, key is my 100 and my value 101. So if I am trying to remove the value for 1100, then I traverse the linked list, and then once I get this value, then I kind of remove it, or get the previous node, or let's say the previous node. So maybe the previous node to point to null, because that's the end of the linked list, right? We can have the previous node point to null, or let's say we have some node over here. So we do have a node, so it will just point to that node. Okay. So either it points to null or to the node. Now, what would be the problem if it is for 100? So where will this, where is the node pointing to? So for this reason, it's usually a good practice to have a dummy node. So a dummy node that points to all the linked lists. So this will be useful if, so this is kind of an edge case, I'd say. So in every situation, let's have a dummy node. So with a 100 as the key. So this is a dummy node. Let's say 101 as the key. We will also have a dummy node, okay, which is pointing to, okay. So all the linked lists. And then when you have a dummy node like this, what will happen is, so you find this, and this pointer will then point over to this node, right? So if you are trying to remove this, so here this pointer will directly point to the next node over here. And our coding can be a little bit better in that situation. Okay. So now, now let's try to then taking all these conditions, let's try to code this. Okay. Okay, so that's my hash map. And if we go over here to the question once more, so we can kind of copy this code here and just put it for now as a placeholder. Okay. Before even completing this code, what we need to do is definitely define, first things first, we need to define a linked list. So let's try to define a linked list class. So class list, linked list node. Okay. So class linked list node, and we can define it as, take the default value. So def, and then initialize init, and then self, switching self, comma, key equals to -1, and then a value. So linked list is defined with a key and a value, right? So let's try to have this default ones as a -1 and -1. Okay. Then let's define self dot, yeah, this is fine. Self dot key is equals to key, value is equals to value, and self dot next is basically none. Okay. So then it's kind of my constructor is initialized with key equals to -1 and value equals to -1. So this basically creates a dummy node, right? Okay, so now we can move on to my hash map. Okay, so the hash map class. So let's have a class hash map, and probably I'll make a little modification here. Call this call this. We'll do a def init and then self. Okay, so that's how I'm defining my constructor. So as I mentioned, my self.size or my size would be a max of 1000. Okay, so this is an array or kind of an array between 0 to 999, right? And then I will have self.map. So this is what? This is actually initializing all the keys with a dummy array. So here I can have a list or linked list actually. So we can call this class linked list node. Yes, so this is fine. So linked list node for I in range self dot size. So that's definitely the 1000 value. And this is initializing the array to dummy node. So these are dummy nodes, right? Okay, so now we can define a hash function. So why do we define a hash function? It's just because we have to use this modulus value a lot many times. So we can use self.key and that return key and then a modulus of self.size, right? So that defines, so the purpose of this key is purpose of the key to an index. So it's basically, you understand this, right? So it's map a key to an index between 0 to 999, right? Okay, now yeah, so kind of define. Now we can go ahead and to take complete the put method. So put, we have self key and value, and modify this a little bit. So just to be specific, my key is an integer and my value is an integer, and it's going to return me a none. Right. So it's going to return me a none. So here we are inserting or updating a value. So insert update a value, right? Or let's say a key value to be specific, a key value pair. Okay. So index equals to self underscore hash, and then the key is fine. So we are hashing this key, right? So that goes into the index, and then previous equals to, we can probably mention this as find previous. Okay. So we can have a find previous helper method. Okay. or we can also go it with the suggestion probably. So self previous equals to self dot mat index. Yeah, this is fine. So previous equals to self dot map index. So this is actually again a dummy node, right? So this is a dummy head. Let's call this a dummy head, right? It's the starting point at the index, right? So it's basically kind of, so this is this one over here, right? So that's the dummy head. Previous equals to dummy head and index, while previous dot next. So if previous dot next equals to key, so if I find the key, then I return, then previous dot next dot value. So the next dot value equals to, so this is how we are traversing the, uh, linked list. Okay? And then finally previous equals to previous dot next, and then we can return the, we can also, oh, let's not, it's fine because we're not calling. So that's okay. And then previous equals to previous dot. Previous dot next, we are calling the linked list function or the linked list node. If key is not found, then we create a node and link it. So this is basically if we don't find a key. So if we don't find a key, then we link it to the node, right? And if it exists, and if it exists, then we can also use the update value with previous dot next dot value, right? Okay, I think this should be good enough for the put method, and then now define the def get. Okay, so we are trying to find a get value which has to return an integer. Okay, so index equals to, so we again find the hash value, so that's where the index goes. So which returns the previous node before the target node. So with this, previous equals to, so we kind of put the previous node to the same index node, that's the beginning. And then with doing previous dot next, we are trying to return the previous node, or we are trying to return the previous node before the target node. So whatever, so we need to return this section right over here. So this can be target node. So we return the previous node before the target node. Okay. So return previous next value. This is the return value. That's fine. And then finally go over def remove. Okay. So again we go over with the key, and the same method applies. Index hashing the index, and then we determine, we put the previous equals to self dot map dot index, and then while we are trying to find the, or while previous equals to next, make this modification of it. But this is not none. This previous dot next is not none, then we can use previous dot next equals to previous next, which is basically unlink the node. So else return 1 time. Check. Check this code. And here value, we can okay, this one right here. So type in, yeah. Okay, that's fine. And then I should put hashmap equals to my hashmap. Okay, and then hashmap dot put. So let's call the value put 1 comma 10. Hashmap dot put and then comma let's do 20 maybe. Okay, and then you can check if it's getting it right. So hashmap get 1 and 101. Hashmap remove 1 and it's not found. So I don't know where over here. check where the error is coming over here. Okay, so still will do that, I guess. So if we can go back, go back, because that's my default value which I missed. Okay, so here and then okay, so it's kind of it's working, and that's kind of the end of the video.